Hello physics, greetings from my kitchen. So I thought I would go through some of this packet with you because a lot of people have had some questions. So let's go to her here. I thought I would start on this page here where you have this multiple choice. You're saying which vector represents direction of the force vector. So the first thing you want to think about is the direction that it's moving. In the previous page, it says that it's moving clockwise. So if we think of it moving clockwise, that would be in this direction. Okay. Um, so if we're moving clockwise, the object is moving in that direction. And so which vector represents the direction of the force when the object is located at point A? Okay, so at point A on the circle, the object wants to move this direction, right? But you would have to apply a force opposite of that motion to make it move around the circle. So exactly opposite, you would have to be pointing towards the center of the circle because you would have to overcome that. So you should get D for that answer right there. Okay, for number 2, which one represents the direction of the force vector when it's located at point C? Again, you've been learning about how force vectors actually, for circular motion, point towards the center of the circle. So for C, it would point to the center of the circle, which would be option B. All right, for question 3, which vector represents the direction of the velocity vector when the object is located at point B? Okay, so if you're looking at point B, the object wants to keep moving off on a tangent, right? So its velocity is actually this direction because its inertia is always in a straight line motion. And that's why your velocity vector, different from force, your velocity vector for that one would point in that direction. So you would choose D for that one because it's pointing straight down. For number 4, when we're looking at the object at point C, we would say that our velocity vector is A, it's pointing outward like that. For 5, which represents the direction of the acceleration when the object is located at point B? Okay, so remember Newton's second law of force equals mass times acceleration. Force and acceleration are always in the same direction. So if we are at point B on our circle, for point B, our force vector, remember the force vectors point directly toward the center, right? Center seeking. So our force and our acceleration vector would both point in the same direction. So it's going to point right towards the center of the circle. So we would choose C for this one. Okay, so for our story here about Rex Things and Doris Locked, fun names, right? It goes through this whole story about Rex making a rapid right-hand turn, and you have to say who's correct for the arguments. And of course, Doris is correct. There's not an outward force. Doris is just experiencing inertia. So she goes flying into Rex, not because of any sort of force, but she just continues in her straight line motion as he turns the car. So that's why she's correct. So if you'd like a really thorough answer for this, you could say this. Doris is correct. There's no outward force. Doris continues her straight line motion. Rex turned the car, so it appears as though Doris is being forced towards Rex, but it's really just her inertia. So your next one is about Carolette, who's learning how to drive. Okay, she turns the wheel to make a left-hand turn, but her car continues in a straight line across the ice. Anytime you hear about something continuing straight, you should always think inertia immediately. So there's 2 teachers apparently in the car, and you have to say which one is the physics teacher, which one's correct, and that would be teacher A, because teacher A says that the lack of friction between the tires and the ice results in a balanced force, meaning there's no net force, so the car keeps moving in a straight line motion. Okay. Next up, you learned about the F word in physics, which is centrifugal force. The F in centrifugal force stands for fake because it's not real. When people talk about centrifugal force, they're talking about the force pushing you outward as you're moving around a circle. That's not real because it's really just inertia. Okay. Then in the next part here, you were looking at some math and the math related to just circular motion. I misquoted Blake here. I said physics is easy, but really his quote is that physics is not that hard. Thankfully, he corrected me, so thankfully that's been clarified for us, so we could just cross out my mistake here. Thank you, Blake. Okay, so let's just talk through these couple right here. Analytical is practicing a centripetal force demonstration at home, which you could as well, with a bucket and a rope. Well, we did this in class as well. Okay. She spins it when it's half full and when it's quarter full. So which would require more force? So I'm hoping that this is a pretty easy one for you. You could say when it's half full, it would take more force. And the reason behind that is because you'd be applying Newton's second law here, that force equals mass times acceleration, right? So you'd be saying that the greater the mass, the greater the force, right? Simple relationship there. Number 2, the Lincoln and the Yugo are making a turn. The Lincoln is 4 times more massive. They make the turn at the same speed. How do their forces compare? Okay, the Lincoln has a greater force because of the greater mass, right? It takes more force to change the direction of something that has more mass. For the Cajun Cliffhanger, number 3, a ride that used to exist at Great America, or you might have ridden on like the, I don't know what it's called. It was the Gravitron at one time, but it's that spinning ride at the fair. So the question is, what effect does doubling the speed have on the centripetal force? Remember, the centripetal force is the center-seeking force. Double the speed means that your force is 4 times greater because you had this relationship in your math problems here that force equals mv squared over r. So if you double the speed, that means that your force is going to be 4 times greater because your velocity is squared in this problem. Okay, for number 4, determine the centripetal force acting on a 40-kilogram child who makes 10 revolutions around the cliffhanger in 29.3 seconds. And so I would start here by listing what I know. M, apparently it's not going to type. M equals 40 kilograms. And I know also that my radius equals 2.9 meters. And I also know that my period, or my capital T, the period, is equal to 2.93 seconds. I know you're saying it says 29.3 right there, but it's 10 revolutions in 29.3 seconds. So that means it's 2.93 seconds for 1 revolution. Okay. And then you have to just think about what equation you're working with here. So you're going to try and find the centripetal force, okay? Centripetal force. So for this, you're going to use that equation, just our same regular old equation, F net equals mass times acceleration, equals mass times acceleration, okay? But now we're talking about circular motion here, so we have to use circular acceleration. And circular acceleration is v squared over r, okay? We don't have the velocity, so we can't use that exactly. So velocity is 2 pi r over t. So you're going to plug in your info there because you know the radius, you know the period, and we know pi obviously. So we can plug in our values for that right there. So you end up with this, 2 pi times 2.9 over 2.93, and you end up with a velocity of 6.92. Which does not finish our problem for us because we have to do v squared over r to get our acceleration. So we end up with an acceleration which is v squared over r and ends up being 13.3. Whoops, 13.3 for our acceleration, meters per second squared. Okay. So after we've gotten our acceleration of 13.3, then we're just going to plug it into F equals m times a. Your mass, remember, is 40 kilograms. So you're going to take 40 times 13.3, and you end up with a force of 533 newtons. You can tell I'm not such a great screenwriter here, but you get the idea. So then you're on to the last chunk of this, which